going to look at this thing called general solutions. Now, when they wrote this new syllabus, it wasn't clear whether general solutions was still in the syllabus or not. Now, general solutions used to be a lot more formalised than what it is now. So what I'm going to do is I'm going to go through and show you the formal definition of general solutions, but then when we do our examples, I'll also show you what you can get away with if you don't want to use the formal ones. But let's just create them. So if we want to solve x equals sine theta, and we want a general solution, so we're not restricting it between 0 and 2 pi, for instance. We want a formula that would create every possible solution. It all depends, of course, whether x is positive or negative, because that will determine which quadrants we're in. So let's assume x is a positive number. Now, if x is a positive number, we know we're in the first quadrant. The angle, that acute angle, would be whatever the inverse sine of x is. That would get us the angle. The other possibility is that it's in the second quadrant. But again, the acute angle would still be the inverse sine of x. So we could say, well, the answer is either going to be the inverse sine of x or pi minus the inverse sine of x. That would be our two possibilities. But if x is a negative number, what happens? Well, if x is a negative number, then I know I'm in the third quadrant, but it's not going to be the inverse sine of x. It's going to be the inverse sine of negative x. So remember, this has to be an acute angle. But if x is negative, the inverse sine of x would give me a negative acute angle, not an acute angle. So therefore I need the inverse sine of negative x to get an acute angle. And in the fourth quadrant, same deal. So we end up with pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. But we know inverse sine's an odd function, so I can now rewrite that as pi minus the inverse sine of x, same answer as I got over here, or 2 pi plus the inverse sine of x, which is actually the same as the first one. As we go around the circle, we just add 2 pi to each answer. Now what this means is it actually does not matter whether x is positive or x is negative. I'm going to get inverse sine of x or pi minus the inverse sine of x. So to generalize this, I can say, well, if I've got sine theta equals x, that's what I want to solve, then theta will be pi k, right, because it's happening every pi, so I've got 0 here, then pi, the next one was 2 pi, so that pi is cycling every multiple pi, but then it's plus or minus, depending, the inverse sine of x. And that's why I put in this minus 1 to the power of k, because that will control whether it's a plus or a minus. If k ends up being an odd number, it's minus. If k ends up being an even number, it's plus. Because look at our formula here. When it was an odd number, 1 pi, we ended up with a minus. When it was an even number, 2 pi, we ended up with a plus. So that is the formal formula, if you like. As I say, don't panic too much about that. That in itself is not in the syllabus. Right? But that is the formal general solution. Of course, we have to define k. K is some whole number, some integer. Let's create the cosine one. So same idea. What happens when it's positive? Well, in the first quadrant, it'll inverse cos of x, but now it'll be the fourth quadrant for positive. My two answers, inverse cos of x or 2 pi minus inverse cos of x. What happens if it's negative? So I'll be in the second quadrant. Same idea. Now that x is negative, I have to get inverse cos of negative x to be the acute angle. And in the third quadrant, my two possibilities then are pi minus the inverse cos of minus x, or pi plus the inverse cos of negative x. Using the relationship we saw yesterday, I can now rewrite that, and we end up with exactly the same answers as we got before. So again, it does not matter whether x is positive or negative. So we can create a formula for cos where we get 2 pi k, but in this case it's just plus or minus the inverse cos of x. We've got inverse cos of x, then 2 pi minus the inverse cos of x. But then if I was to add 2 pi to each of those solutions, I'd get 2 pi plus inverse cos of x, and then 4 pi minus. Add 2 pi again, I'd get 4 pi plus 6 pi minus. So we're always getting multiples of 2 pi, both the plus and the minus of the inverse cos x. Why is that? Well, if you have a look at this diagram here, at the very first ones, because it's either side of the 2 pi. Let's create one for tan. Go through the same idea again, but this time with tan, it's the first and the third quadrant. So I get inverse tan of x, or pi plus the inverse tan of x. And if it's negative, I'll be in the second or the fourth quadrant. But again, it has to be inverse tan of negative x this time. So I get pi minus the inverse tan of negative x, 2 pi minus the inverse tan of negative x. That, playing around with it, inverse tan is an odd function. I get pi plus inverse tan of x, same answer as I got before. 2 pi plus the inverse tan of x, well, that's the same answer. I've just added 2 pi. I've gone around the circle once. Yet again, it does not matter whether x is positive or negative. So I, in this case, get pi k. So multiples of pi, just simply plus. It's always plus. There's never negatives on this one. So it's always plus. Let's do some, and then I'll show you what you can get away with. You don't have to panic and remember those formal ones. It's just showing you what the formal general solutions are. If I want to solve this formally, I would use this formula. Pi k plus minus 1 to the power of k, inverse sine of root 3 on 2, where k is some integer. And then I'd go, well, what's the inverse sine of root 3 on 2? I get pi on 3. So that's the formal one where I can write it as one thing. There it is, pi k plus minus 1 to the power of k pi on 3. What can you get away with? Well, what you can get away with is just solve it as normal. Sine theta equals root 3 on 2. I'd say, oh, it's in the first or the second quadrant. So therefore I get pi on 3 or 2 pi on 3. And then all I simply do is go, oh, plus 2 pi k. Because I can go around the circle. I can go around the circle. It's writing it as two things instead of one thing. But it's okay for the solution under the new syllabus. So if you want to play around with the formal one, by all means. But as I say, this is what you can get away with for an answer. It is a general solution. It generalizes all the possible answers. So solve it just as normal, but simply add multiples of 2 pi to it. And remember to specify that k has to be a whole number, has to be an integer. So if I did the cosine one, then the formal one, I'd write it like that. 2 pi k plus or minus the inverse cos of minus 1 on root 2, which is 3 pi on 4, was our answer. So I'd write it like that. But of course we can get away with going, well, cos theta is minus 1 on root 2. I'm in the second or the third quadrant. So I get 3 pi on 4 or 5 pi on 4. But then again, I could add 2 pi to each of those solutions. Well, let's do a tan one. So tan theta is 1 on root 3. Formalize it. It would be pi k plus inverse tan of 1 on root 3. And that is pi on 6. Doing it the other way, I'd say, and this is the difference here with tan. Because its period's only pi, not 2 pi, I actually only need one solution for this. Because I would have gone first quadrant and third quadrant, but if the period's pi, then I really only need to worry about the first two quadrants. And the only answer is in the first quadrant. So I just do one of them. So tan theta is 1 on root 3, so it'll just be pi on 6 plus pi k. And again, where k is integer. So that's interesting. Doing it this way, I actually get the same as the formal one for tan. The other ones, it splits it up into two possibilities rather than having one possibility. Now, the next few examples are probably just going a little bit crazy. In the old syllabus, you might see questions like this. I don't think we're going to see ones like this anymore in the HSC because we're not formalising it as much as we did before. We used to have things like this. So sine theta is the sine of 5 pi on 7. We can still do it. There it is in the formal solution. You get pi k plus minus 1 with k, inverse sine of the sine of 5 pi on 7. Well, the inverse sine of the sine, remember, we can only get angles that are acute or negative acute angles when we're talking about inverse sine. So we can't get the answer 5 pi on 7. 5 pi on 7, that's in the second quadrant, so it would be positive. So it's a positive acute angle. The acute angle is 2 pi on 7. That would be the solution to that. I didn't do that one the other way because I don't think we're going to get ones like that. This is just me going crazy. Alright, cos of 2x is cos pi on 9. So using the formal solution, well, 2x is now 2 pi k plus or minus inverse cos of pi on 9. That one's okay because pi on 9 is an acute angle anyway. It's in the first quadrant. So that will cancel. But that's 2x divided by 2. I would get that answer. Cos 4x is equal to cos x. 4x is 2 pi k plus or minus the inverse cos of cos x. now it depends what happens if x is positive or x is negative, because that's going to change this one. Let's assume it's positive. So I would get 4x minus plus, move it to the other side, equals 2 pi k. So 3x is 2 pi k, x is 2 pi k on 3, or 5x is 2 pi k, because if I've added that on I get 5. So the other possibility is 2 pi k on 5, but hang on a sec, cosine's an even function. So cos x is cos negative x, thus inverse cos of cos x is the same as the inverse cos of cos negative x, which equals negative x as x is less than 0. So I actually don't need to worry about this other case. That's me now proving that they give the same one rather than actually going through the whole working out. My answer, here we go. Alright, let's do another one. Sine 4x is sine x. Wow. Again, I'm going to have this situation. Let's treat positives. 4x will be pi k plus that. But now I have to worry about whether k is an odd number or whether k is an even number, because that will change whether that's negative or positive. So if k is odd, 4x will be pi k minus x. Moving it over, I get this wonderful solution for x. But if it's even, then it becomes 3x is pi k, and I get that beautiful solution. But if x, that's just if x is positive. If x is negative, now inverse sine of sine x is x, so that'll get the same results as when x is greater than 0, so I've got the same answers. So there's no need to check positive and negative for inverse sine. I have my answers. I bet you're glad we don't go to that depth anymore, aren't you? There's a handout there, because it's not. When they first wrote the textbook, they didn't have an exercise on it, because they thought, well, it's not listed in the syllabus. And the big question was asked this very first year of the new course. People go, what, are they or aren't they? And there was this really vague thing from Nessa saying, oh, well, yeah, no, look, it's not actually said in the syllabus, but it's sort of implied you might have to write a general solution. So very, very vague. That's what I'm saying. You can just get away with it, plus 2 pi k now. They're not expecting us to use those formal ones, but this handout is something then that the textbook put together this exercise and said, well, look, here's an additional exercise on general solutions just in case. Let's have a bit of a play.